Welcome again to Engineers Newsletter Live. I'm Jeannie Harshaw from Trane's System and Application Engineering Group, and today we'll be discussing variable refrigerant flow systems. This course is approved by the U.S. Green Building Council for 1.5 continuing education hours toward the LEED Credential Maintenance Program. After attending today's program, LEED professionals should submit their hours to USGBC. Today's program is also registered with the American Institute of Architects Continuing Education System and qualifies for Health, Safety, and Welfare credit. AIA members, please provide your member number to your local host before leaving today's session. And professional engineers, please check your state's rules to see if credit for attending today's program can be applied to your engineer's continuing education requirements. Variable refrigerant flow systems have been around for decades, but their widespread use in the United States is still relatively new. As design engineers consider using these systems, we often get asked for help in understanding how to apply them with respect to building codes, industry standards, and common practice. Today, we'll discuss some of the more common application challenges and ways to address each one. Trane Applications engineers Eric Sturm, Paul Solberg, Dave Guckelberger, and John Murphy will take us through our discussion today. Eric, can you get us started?
Before we get into the application challenges, let's start with an overview to make sure everyone understands what a VRF system is. A VRF system is simply a direct expansion air conditioning system that connects multiple indoor units on a single refrigerant circuit. The indoor units are often in or very near the spaces they're designed to condition, so there's little ductwork, if any at all. There are cooling-only systems, heat pump systems, and heat recovery systems. The latter two are able to provide heating. VRF systems include an outdoor unit, a refrigerant control device for heat recovery systems, indoor units, controls, and refrigerant piping. We'll talk about each of these in greater detail throughout the broadcast. First, let's spend some time looking at the outdoor unit, its components, and how it works. The outdoor unit typically contains one or several compressors. Because there are multiple indoor units with changing loads and usage, variable speed control is used to vary the amount of refrigerant flowing through the system. Today, most units contain at least one variable speed compressor to provide modulation. The name variable refrigerant flow comes from this ability to modulate the rate of refrigerant that flows through the system. The outdoor unit also contains a heat exchanger, which serves as a condenser in the cooling mode and an evaporator in the heating mode, and heat rejection fans. An additional heat exchanger, or intercooler, is provided to increase subcooling in the cooling mode and heat output in the heating mode. The heat rejection fans may be variable speed, multi-speed, or staged. An expansion device is included to lower the refrigerant pressure before the outdoor coil when operating in the heating mode. An oil separator is installed downstream of the compressor to reduce the amount of oil leaving the outdoor unit. This allows the system to run at very low loads and accommodate long refrigerant line lengths. During cooling operation, refrigerant is compressed by the machine's compressors within the outdoor unit. The hot, high-pressure refrigerant passes through the heat exchanger, which is currently running as a condenser to reject heat. The refrigerant is then distributed to the indoor expansion devices and evaporators to remove heat from the spaces. During heating operation, heat pump VRF systems reverse their cycle and refrigerant flow to provide heating. In this mode, the hot, high-pressure refrigerant is sent to the indoor unit heat exchangers, which serve as condensers. Heat is added to the spaces. The refrigerant then flows to the outdoor unit, passes through an expansion device, and through the outdoor coil. In this mode, the heat exchanger in the outdoor unit serves as the evaporator. Heat pump VRF systems either operate to provide cooling or heating. They cannot provide both at the same time. On the other hand, heat recovery systems have the ability to provide simultaneous heating and cooling because both high-pressure gas and liquid refrigerant are available to the indoor units. The heat recovery control module, shown here as a gray box, enables the system to provide both heating and cooling simultaneously. For heat recovery systems, the control module acts like traffic police in that it's able to direct either hot gas or liquid refrigerant to the individual indoor units. Of course, this requires sophisticated controls that are able to relay the desire for heating or cooling to the refrigerant traffic police. The module is connected to the outdoor unit, and a series of refrigerant lines is run to each indoor unit. In this example, each indoor unit is providing warm supply air to each space. As conditions change, some zones will require cooling. The heat recovery control module allows some units to cool and others to remain heating at the same time. 2 zones now require cooling, while the remaining zones continue to need heat. The heat recovery control module is able to route low-temperature liquid refrigerant to the indoor units that require cooling while sending high-temperature gas to the indoor units that need heat. The heat recovery control module can also route refrigerant from one indoor unit to another, bypassing the outdoor unit. This works by transferring energy between indoor units that are working in opposing modes. The setup proves to be really flexible. As you may have noticed in these diagrams, there are many styles of indoor unit that can be selected for a specific application, and they usually range from a cooling capacity of several MBH to a few tons. Often, many different configurations are available. Each has a fan or multiple fans that may be variable speed, stepped, or constant speed. And of course, each includes a coil and an expansion valve for cooling mode. Some models are designed to fit in small closets or above the ceiling and discharge directly into the occupied space. Other units require small sections of duct to discharge air into the spaces. Some units might discharge enough air requiring several diffusers, and some models can even automatically change their flow direction. Controls are key to a VRF system and include zone level, building level, and system controls that ensure proper outdoor and indoor unit operation. At the zone level, a wired or wireless remote control allows individual comfort management. Each component in the system, the outdoor unit, indoor unit, and heat recovery control module, are also connected by a series of refrigerant lines. Depending on the number of indoor and outdoor units, the quantity, length, and the lift of these refrigerant lines can be substantial. The sum total of the lines can be thousands of feet. This allows outdoor units to be placed a significant distance from indoor units or even on the roof of multi-story buildings. So now we have an understanding of what the system looks like, the components that make it up. Paul, can you take us deeper into system operation?
Sure can, Eric. There are 3 basic types of outdoor units. At the small end of the VRF capacity scale are outdoor units 5 tons and under, commonly referred to as mini VRF. These models are typically available with single-phase power, making them suitable for residential applications. They are typically available as heat pumps and are only able to be connected to a small number of indoor units. They cannot be combined to form larger capacity outdoor systems. For conventional VRF systems, probably the most common type of outdoor unit is an air-cooled model depicted here. These units are offered in 3-phase power and, depending on the size, will have 1 or 2 upflow discharge condenser fans. They are modular, with single units offered in distinct capacity increments, typically from 6 through 14 tons. Individual outdoor units can be combined together into 2 or 3 unit modules for total capacity up to around 36 tons, depending on the manufacturer. Buildings larger than 36 tons can still use VRF, but would need to be split up to be served by more than one system. Finally, VRF outdoor units are also available for water-cooled application. They are similar to air-cooled models with regard to voltage, capacity increments, and modularity, and are also available in either heat pump or heat recovery application. The primary difference is the outdoor unit uses water rather than air to exchange energy. Water-cooled units can be installed with either a ground heat exchanger or a cooling tower and boiler, and they can be installed either indoors or outdoors. Now let's look at the variety of indoor units that complete a VRF system. They are commonly categorized as ducted or non-ducted models. All models are offered in a wide range of capacities with airflow adjustable to meet the given application. Ceiling cassettes are non-ducted models that are designed to be recessed into the ceiling. They are compact and feature decorative panels within hidden return air filters that install flush with the ceiling. Four-way cassettes are commonly used in conference rooms with airflow patterns that can be customized by allowing blades to be individually adjusted or even permanently closed. One-way and two-way models are suitable for hallways or along the perimeter walls. High-wall models, traditionally thought of as mini-splits, are another non-ducted indoor unit available for VRF systems. Suitable for applications with free wall space such as residences, hotel rooms, and offices, they also contain air vanes that are adjustable. Now, let's talk about indoor units that can be ducted. Short duct runs can be connected to the supply side of indoor units located throughout a building, allowing them to distribute air to larger zones or multiple rooms. For example, there are a number of designs of concealed indoor units that look much like conventional fan coils. They are intended to be concealed in ceiling spaces or soffits. One common style is often called slim duct due to its low height profile, often 8 inches or less, making them suitable for hotel rooms and assisted living facilities. Slim duct models have limited external static pressure capability and are intended for applications where supply and return ducting is minimal. Mid and high static pressure concealed units are available in larger capacities and can be installed with longer supply and return duct runs. Like the slim duct models, they are intended to be concealed in ceiling spaces. Common applications include larger conference rooms and lobby areas where 2 or more supply ducts will provide uniform air distribution and comfort, and even adjacent rooms that have common demand. Finally, some VRF systems are even installed with residential-style air handlers, installed either horizontally or vertically. Common applications include retrofit projects with available closet, attic, or equipment room space. Each of these VRF indoor units uses an electronic expansion valve to maintain suction temperature and comfort. And of course, the indoor units serve as evaporators in the cooling mode, which results in the formation of condensate on the coil that must be managed. So they commonly include either an integral or field-installed condensate pump. Each VRF indoor unit needs to be individually piped to a condensate drain or disposal system. Now let's look at the controls that tie the system together. I'll begin with a small building that uses a single VRF system. First, it must be noted that all VRF manufacturers, due to their complex communication requirements, currently use proprietary controls. Most ductless indoor units, like the cassette or high-wall models, utilize a wireless remote control similar to a TV remote. They offer basic capabilities such as on-off, operating mode, fan speed, airflow, and temperature set point. Through multi-channel logic, one wireless remote device can even control multiple indoor units. Because they are out of sight, ducted indoor units are normally installed with a wired remote control. These wired controllers typically offer additional capabilities such as weekly scheduling, temperature limit setting, and error display. A single device can control multiple indoor units as a group. A wireless remote could be used with a hidden ducted unit if a remote signal receiver were installed. For larger buildings with several individual VRF systems, a VRF controller can be used. These controllers are typically capable of more complex scheduling, grouping of zones, for example by floor, and have the ability to override or limit settings in individual zones. The VRF system controller may add the capability for complex monitoring and error management, and also allows remote access through the internet. Finally, using a system controller that uses BACnet communication protocol allows a designer to interconnect the VRF system into any compatible enterprise control system, allowing integration with other systems throughout a building or campus. When we put all these components together, we end up with a complete VRF system. Earlier, Eric discussed the difference between a heat pump and heat recovery VRF system. In a heat pump system, the outdoor unit can only be in heating or in cooling mode. It cannot satisfy indoor spaces that have conflicting comfort needs. For example, on a cool March morning, when people arrive at work, they generally will need heat to offset the overnight building cool down. So the system goes into heating mode and satisfies the occupants. But look what happens to the top zone and east-facing conference room with lots of glass later that morning. The occupants in the conference room want cooling, but the system is still in heating. The unit serving that conference room will not begin to cool until all the other zones are satisfied, and the outdoor unit can go into cooling mode. One way to address this issue could be to add a system selector switch to the outdoor unit, perhaps in the manager's office, that will control the mode of the outdoor unit, either heating, cooling, or off. This can also be accomplished with most of the system level controls we discussed a few minutes ago. Although this manual changeover will satisfy our conference room, it is at the sacrifice of comfort in the other 5 zones. But a solution to this application dilemma may be to specify this as a heat recovery system, which is capable of simultaneously heating and cooling. With simultaneous heating and cooling, discharge gas, liquid, and suction refrigerant paths must be available to the individual indoor units. To allow this, a component called a heat recovery control unit is required. It's the traffic police component that Eric mentioned. This is an example of one manufacturer's model. These devices have 3 refrigerant pipes connecting it to the outdoor unit, one for discharge gas, one for suction gas, and one for liquid, and there are 2 refrigerant pipes connecting the indoor units to this module, one vapor and one liquid. The system control determines if the indoor vapor port is connected to the discharge or the suction gas, based on whether it's in cooling or heating mode. But the heat recovery control unit can even do more. It can take the waste liquid from a heating zone and direct it to a cooling zone. This is how simultaneous heating and cooling is accomplished. The heat recovery unit can be located anywhere. If it's located at the outdoor unit, the system will be 2-pipe. If it's at the indoor unit, it's a 3-pipe system. If it's somewhere in between, it's a hybrid. Each manufacturer has chosen a design based on trade-offs between efficiency, comfort, and installed cost. Now let's take a closer look at how a heat recovery VRF system provides simultaneous heating and cooling. Here I show a hypothetical system that has 6 equivalent zones, 2 of which are in cooling and 4 in heating. Focus on the bottom 2 zones, one requiring heating and the other cooling. The zone at the bottom requires 2 tons flow of discharge gas to satisfy the zone heating load and returns 2 tons of condensed liquid refrigerant back to the heat recovery control module. The zone above requires 2 tons of liquid refrigerant to satisfy the zone's cooling load. There it is inside the heat recovery control module. So let's steal it from my neighbor. After evaporating in the indoor unit that needs the cooling, 2 tons of suction gas is returned to the heat recovery control module and back to the outdoor unit. We have converted 2 tons of discharge gas to heating and used its condensed liquid for 2 tons of cooling. So 4 tons of benefit for 2 tons of energy. This is also an opportunity to introduce another characteristic of a VRF system, commonly referred to as combination ratio. The combination ratio is the sum of the indoor tonnages divided by the sum of the connected outdoor unit tonnages. The maximum this ratio can be is dependent on manufacturer, but is in the range of 1.2 to 1.5. Staying under the combination ratio prevents 2 problems. First, it prevents an imbalance in the refrigerant charge when the system is in total cooling or total heating. If this were to occur, the unit would shut down on a safety. Second, it allows for some zone load diversity inherent in most buildings due to varying occupancy patterns and loads. Indoor units are normally cycling on and off based on individual zone requirements. Because the combined loads of the indoor units aren't constant, it allows the total connected capacity of the indoor units to exceed the capacity of the outdoor unit. In our example, the total combined capacity of the indoor units is 10 tons, and it is connected to an 8-ton outdoor unit, which is a 125% combination ratio. But use caution. Designing in excess of the manufacturer's combination ratio may risk comfort problems on days with extreme temperatures combined with peak heating or cooling loads. The flexibility of VRF systems prevents lots of design options, but there are some practical limits to just how big a system can be. One of these limitations is refrigerant piping. Each manufacturer defines maximum limits for the requirements of refrigerant piping. The total elevation limit is the maximum vertical distance between outdoor unit and the furthest indoor unit. Sometimes this can be further limited if the outdoor unit is installed on the ground and needs to pump liquid refrigerant upwards. There is also a maximum separation distance between indoor units on a single circuit. And there's a maximum separation between the first branch and the furthest of the indoor units. And the sum total pipe length of an individual VRF refrigerant circuit is limited to 3,000 feet, depending on the manufacturer. That's a lot of pipe. Of course, that also results in large volume of refrigerant in the system, which will be addressed later during this presentation when we discuss compliance with ASHRAE Standard 15. Extremely long piping runs may require some adjustments to the size of the refrigerant lines to compensate for capacity or efficiency loss. Some designers also choose to oversize indoor units located long distance from the outdoor unit, but this can lead to a domino effect in which this increased indoor unit capacity leads to upsizing the outdoor unit. Looking at all this refrigerant pipe might have you asking, what about oil return? This is a legitimate concern and an obvious question. Well, let's take a look at how VRF manufacturers handle this. First, the compressors must be designed with adequate internal storage capacity, so they have large sumps. Next, the addition of an oil separator helps capture most of the oil that is pumped out of the compressor and is injected back to the compressor. Yet since the separator isn't 100% effective, some oil will still circulate out in the system. So VRF systems have a built-in oil recovery cycle, a flush cycle if you will, which is initiated based on compressor runtime, frequency, and other factors. When the oil recovery cycle begins, an expansion valve will open to a minimum setting and the compressor will speed up to flush the oil back to the compressor in the outdoor unit. This is a good spot to elaborate on the VRF variable speed compressor. Most VRF systems today feature one or more inverter-driven compressors. Most compressors have a design range similar to what I'm showing here. In this example, the inverter drive operates between 20 and 140 Hertz, which translates to 1200 to 8400 RPM. In the cooling mode, there's an optimum or most efficient speed for an inverter compressor. In this case, the optimum speed for cooling is between 2000 and 4500 RPM. In heating, this optimum range may be a bit higher. Now, as more capacity is needed to balance the load of the system, the compressor speeds up. This increase in compressor speed is what allows VRF systems to overcome many of the negative conditions working against them, like long piping lengths and high combination ratios. But it also may push the compressor out of its most efficient operating range. Defrost. Defrost is a necessary evil for air source systems acting as heat pumps. During heating mode, the outdoor unit is working as an evaporator. Depending on the outdoor temperature and humidity, frost can form on the outdoor coil. Manufacturers use algorithms to determine when performance has degraded enough to require a defrost cycle. The system actually returns to operate in the cooling mode for several minutes, which means the outdoor unit becomes a condenser and melts away the frost. A defrost cycle has a negative impact on both comfort and energy efficiency. On a VR system with multiple outdoor units, comfort can be maintained by using a rotational defrost pattern, which means that one or two of the outdoor units continue operating in heating mode while one goes through its defrost cycle. For mini VRF or for single outdoor VRF systems, rotational defrost isn't possible. In these systems, the indoor fans are turned off to reduce comfort issues as the system switches to cooling. Comfort needs to be further considered because the time-weighted capacity of a system is reduced due to the defrost cycle. This slide shows one manufacturer's capacity correction because of the defrost cycle. Defrost affects energy use also. At best, it provides no useful heating, but still runs the compressors to thaw the outdoor coil. There's little that can be done to reduce the defrost energy. With some engineering judgment, a chart similar to this could be helpful when implementing the defrost portion of energy modeling. The last challenge I'll talk about is heating loss as the outdoor temperatures drop. We talked earlier about how an inverter compressor will speed up as the load increases, but when the outdoor temperatures drop to 15 or 20 degrees, say, it'll have reached its maximum RPM. At that point, system capacity will begin to drop. But when and just how fast this occurs is a function of system design. But all systems will be impacted to some degree. Most manufacturers catalog performance down to -4F. So the question arises, what happens then? Most VRF units will continue to operate below -4, continuing to lose capacity and efficiency until they shut down on internal protection controls. It should be clear by now that while VRF systems have components in common with other HVA systems, they really are unique. This unique system type provides new opportunities and new challenges. So let's get into some more of these challenges. For example, the ability to connect over 3,000 feet of refrigerant pipe to a single outdoor unit allows tremendous flexibility in the location and distribution of the components that comprise a VRF system. But more refrigerant pipe means more refrigerant. Dave, is it safe to have all that refrigerant pipe in a building?
Yeah, it certainly can be. Safety implications are covered by ASHRAE Standard 15. So let's take a look at how the standard applies to VRF systems. I've divided the content of this section into 3 parts. The approach is to start at a high level by reviewing why Standard 15 is appropriate for VRF systems. Then review the structure of the standard, and finally examine the details using an example case. Okay, so why Standard 15? ASHRAE is one of several organizations that write standards for HVAC equipment. The standards are developed following an ANSI process that requires collaboration and a multi-stage public review. It's tedious and time-consuming, but the result is a well-researched document that outlines the current standard of care. But ASHRAE doesn't have any enforcement authority. To be enforceable, the standard must be incorporated into code. Typically, this is a 2-step process. Model code agencies, such as the International Code Council, look to industry standards and other materials for best practices. They combine these into model codes. The final step is for a state or other governing body to adopt the model code into law. These laws, or codes, are then enforced by the building inspectors. It's important to understand this process because several years can pass between the publication of a standard and its incorporation into a state code. Changes in wording and sometimes intent occur along the way. So, bottom line, when applying Standard 15, be sure to also check the local codes. For states that use the International Mechanical Code, the linkage between Standard 15 and the resulting code is really strong. Section 1101.6 of the IMC states, refrigeration systems shall comply with the requirements of this code and, except as modified by this code, ASHRAE 15. By this reference, all of Standard 15 is included in the IMC and the state codes that adopt it, unless the wording in the IMC conflicts with the standard. To summarize this first section, ASHRAE Standard 15 is not directly enforced, but it is included in part or in whole in most state codes. The process from standard to state code introduces the opportunity for variation, so it's essential to know the code details for the jurisdiction where the equipment will be located. Okay, so once you establish that Standard 15 applies in your jurisdiction, the next step is to look at what Standard 15 requires. A good place to start is with the purpose and scope. Notice the focus on safety. In fact, the name of the standard is Safety Standard for Refrigeration Systems. The material in this standard is intended to promote safeguards by establishing a framework to guide the design of refrigeration systems. Keep this focus on safety in mind when you read the standard. If you're confused about how to interpret a particular section, choosing the path that results in greater safety will generally lead you in the right direction. The next step is to determine in which situations Standard 15 applies. Basically, there are three triggers. The first is new construction. Whenever a refrigeration system is installed in a new building, the design must comply with the current code. Once the building is finished and approved, no further upgrades are required to keep up with revisions in the code unless one of the following changes is made. A modification to an existing system that changes the size or function must comply with the current version of the code. Basically, replacing a failed part with a similar one doesn't require a code review. But adding an additional indoor unit to an existing VRF installation or replacing an existing unit with one that is larger or smaller will trigger a code review. And finally, compliance with the current code is required when a refrigeration system is converted to a different refrigerant. Okay, so now that we know when to apply the standard, we need to figure out how to apply the standard. It's important to realize that Standard 15 applies to all sizes and types of refrigeration equipment, from a small window air conditioner that contains a fraction of a pound of refrigerant to a large chiller containing several thousand pounds of refrigerant. To encompass this broad range, Standard 15 defines restrictions for refrigerant use based on three criteria: building occupancy, system type, and refrigerant safety group. For the purposes of Standard 15, ASHRAE divides occupancies into 7 categories. In practice, the 7 categories can be reduced to 3 types because the same rules apply to public assembly, residential, commercial, and large mercantile. Special rules apply to the last 2 occupancy types, institutional and industrial. Institutional occupancy includes facilities where the occupants have difficulty evacuating, such as hospitals and jails. Refrigerant safety rules are more restrictive for this application. Industrial occupancy is at the other end of the spectrum. Because this type prohibits access by the general public, less restrictive rules apply. Finally, the term mixed occupancy is used when the building contains more than one occupancy type. For example, a hospital that contains a restaurant open to the public could have both institutional and commercial occupancy types. However, different areas of occupancy can only be considered separately if they are isolated from each other by tight-fitting floors, ceilings, and walls with self-closing doors. Plus, the HVAC systems serving the areas must be separate. If this isolation does not exist, then the occupancy with the most stringent requirements governs the entire area. The second criteria is refrigerating system type. The standard classifies systems according to the probability that refrigerant discharged from the equipment will reach the occupants of the building. VRF, rooftop, and water source heat pumps are examples of direct system units. These systems are considered high probability because the refrigerant coil is in the airstream that serves the occupied spaces. The third and final criteria is refrigerant safety. Safety information for refrigerants comes from ASHRAE Standard 34, which is referenced by Standard 15. Standard 34 defines 6 safety groups based on 3 classes of flammability and 2 classes of toxicity. The 3 levels of flammability cover the range from no flame propagation to highly flammable. Class 1 means that the refrigerants do not show flame propagation when tested in air. Due to the increased safety risks of flammable refrigerants, manufacturers primarily look to Class 1 refrigerants for HVAC applications. A subclass 2L was added in 2010 for refrigerants that, while flammable, have a lower flammability risk than other Class 2 refrigerants. it's likely that some future refrigerants will fall into this class. The two levels of toxicity are defined using occupational exposure limit. The occupational exposure limit defines a refrigerant exposure level that is considered safe for most workers. Refrigerants with an OEL of 400 parts per million or greater are Class A. All others are Class B. So when combined, the safety classifications for flammability and toxicity yield the 6 safety groups shown. Most refrigerants used in VRF applications are classified as A1. That is, they are not flammable and they have low toxicity. There's one more key piece of information that comes from ASHRAE Standard 34, refrigerant concentration limit. A unique RCL is established for each refrigerant based on its toxicity, flammability, and oxygen deprivation characteristics. Standard 34 contains a complete listing of refrigerants, including their safety group and RCL. The table shown here is a subset of that information from the 2013 version of the standard. A word of caution about using RCL values directly from Standard 34. RCL is a relatively new metric of refrigerant safety. As a result, the RCL values for many refrigerants were adjusted over the last few revisions of the standard. Some model codes and state codes include RCL values as part of the code text and reference older versions of Standard 34.
So let me pause here and summarize what I've heard so far, Dave. First, Standard 15 certainly applies to these direct systems like VRF, package rooftops, and so on. And its rules are based on occupancy classification, refrigeration system type, and refrigerant safety criteria. But the requirements are not specific to the type of equipment. That is, it doesn't explicitly list rules for a VRF system versus a water chiller. Instead, the standard provides minimum performance requirements.
Yeah, I like what you said about the rules. A lot of engineering judgment is left to the designer responsible for the system. So now that we understand why Standard 15 is important, how it relates to the code, and have a concept of how performance requirements are determined for a given application, let's look at a typical building. The example building is a single-story office with a variety of rooms. All of the rooms, except for those shown in red, are served by our VRF system consisting of 1 outdoor unit and 6 indoor units, 1 per room. The occupancy type is commercial, and it's a high probability system because the refrigerant coil is in the airstream serving the occupied space. The refrigerant is R410A. Standard 34, 2013, categorizes R410A as an A1 refrigerant with an RCL of 26. However, the current version of the International Mechanical Code lists the RCL at 25. This is an example of the code being out of sync with the current standard. For high probability systems, the calculated concentration of refrigerant must not exceed the RCL for all occupancies except institutional and industrial. For institutional occupancies, RCL values are reduced by 50%. Conversely, amounts exceeding the RCL are permitted in industrial occupancies if certain conditions are met. Since our example building is commercial occupancy, refrigerant concentration is limited to 100% of the RCL. The units on RCL are pounds of refrigerant per 1,000 cubic feet. So once the proper RCL value is determined, there are 2 additional steps: determining the pounds of refrigerant that could be released from the system and determining the volume available for dilution. Standard 15 considers the entire charge in the circuit serving the coil to be the amount that will discharge due to a failure. If the room contains distinct, independent refrigeration circuits, use the refrigerant quantity in the largest circuit, not the sum of the refrigerant in all circuits. This is mainly important where parts of more than one refrigeration system share the same dilution volume. For example, if you have a room served by 1 VRF system, but the refrigerant piping from a second system passes over the room, the one with the larger charge should be used to determine compliance with the RCL. If the systems contain different types of refrigerant, both should be checked for compliance. For our example building, all of the indoor units are served by a single circuit. Total charge is the refrigerant charge shipped in the condensing unit, plus any additional charge added on site for refrigerant lines. Because the standard 15 analysis is done before the system is installed, a detailed layout of refrigerant piping must be made in order to facilitate an accurate total charge estimate. For our example system, the total charge estimate is 31 pounds. The next step is to calculate dilution volume. Section 7.3, Volume Calculations, contains several important subsections. The first is non-connecting spaces, which defines how to calculate dilution volume for an unducted refrigeration system in an occupied space. Most VRF applications provide terminal units that are unducted and serve a single space. In this case, dilution volume is limited to the volume of the room. The dimensions of the room, height times width times length, determine the dilution volume. No subtraction is made for furniture or other items in the room. However, any portion of the room that can be closed off must be excluded. For example, a closet space in a bedroom or the bathroom in a hotel room. Via an interpretation, the Standard Committee confirmed that the hotel bathroom volume must be excluded even when the bathroom has a continuously operating exhaust fan supplied with outdoor air from the hallway. The second section in 7.3, Ventilated Spaces, defines how to calculate dilution volume when the refrigerant coil is in an air handler or ducted air distribution system. In this case, dilution volume is the sum of all spaces served by the air handler, provided that those spaces cannot be shut off from the air handler. Plenum volume can also be included in dilution volume as long as it is contiguous and is part of the normal supply or return airflow path. Returning to our example building, the smallest room served by the system is Office 2. Using our estimated system refrigerant quantity of 31 pounds, the room volume of Office 2 yields a refrigerant concentration of 34 pounds per 1,000 cubic feet. This exceeds the RCL of 26 for our application, so it would not be permitted. The conference room is the next smallest room served by the system. The refrigerant concentration for this room is 24.6 pounds per 1,000 cubic feet. This meets the RCL requirement, but it doesn't provide any tolerance in the event that the actual charge exceeds the estimated charge. So what happens when the calculated concentration exceeds the RCL? Standard 15 does provide options for some system types, but for direct systems like VRF, the only viable option is to reduce the refrigerant concentration. So either pick a unit with less refrigerant or increase dilution volume. For our example building, 5 out of the 6 rooms meet the RCL requirement. However, the system would not be allowed because of Office 2. But that doesn't mean VRF can't be used on this building. One solution is to serve Office 2 with a small, separate unit. A direct unit serving a single space will likely have a small enough charge to meet the RCL requirement. A second choice is to replace the single VRF system with 2 smaller systems. Either solution is acceptable as long as the RCL requirement is met for all rooms. So far, the solutions have focused on reducing refrigerant charge. But what about increasing dilution volume? Some sources have suggested that an undercut of the door is sufficient to permit the volume of the adjacent space to be included in the dilution volume. Others have suggested air transfer ducts from room to room or outdoor air ventilation systems are ways to increase dilution volume. The danger of this type of thinking is well stated in an ASHRAE Journal article written by Stephen Duda while he was a member of the Standard 15 Committee. I highly recommend the entire article, which can be found in the July 2012 edition of the journal. In addition to the article, also be sure to review the interpretation listed, which specifically excluded door undercuts and air transfer grills as viable ways of increasing dilution volume. For our example building, a good way to increase dilution volume is to use a ducted VRF unit to serve Office 2 and another room. For ducted units, dilution volume is determined by the ventilated spaces section of Standard 15. As mentioned earlier, this allows all spaces served by the unit to be included in the dilution volume. Meeting the RCL requirement outlined by Standard 15 might be more difficult for VRF systems, but it certainly isn't a showstopper. In addition to RCL, there are other requirements of Standard 15 that apply to VRF systems. For example, there are restrictions on refrigerant use in corridors and lobbies, and requirements for the installation and location of refrigerant piping. These requirements also apply to single evaporator split systems, so you might already be familiar with them. If not, the ASHRAE Journal article I mentioned is an excellent reference source for additional detail on how these sections apply to VRF systems. In summary, Standard 15 applies to all types of refrigeration equipment and all refrigerants. The main difference with VRF systems is the potential for higher refrigerant concentrations in the occupied spaces. If you understand and follow the requirements of Standard 15, VRF systems will be just as safe as any other refrigeration system.
The next topic is complying with energy codes. While codes vary by jurisdiction, today we'll focus our discussion on ASHRAE Standard 90.1, since it's the basis for most model codes. Murph?
While there is certainly a long list of requirements in Standard 90.1, I'm going to discuss just a few of the common questions we get about complying with the standard when using a VRF system. I'll start with the minimum equipment efficiencies and then talk about the fan power limitation, economizers, and exhaust air energy recovery. And as the slide indicates, I'm going to use the 2010 version of the standard for this discussion, since it's the version used in the current model codes as well as the newest version of LEED. But if something has changed in the 2013 version, I'll be sure to point that out too. But before talking about equipment efficiency, it's probably good to point out that Standard 90.1 only includes minimum efficiency requirements when a product has an industry agreed upon test procedure and rating standard. VRF products are different than other air conditioning products because they distribute refrigerant from one outdoor unit to multiple indoor units. Therefore, the rating standards used for traditional air-cooled DX products like HRI 210-240 or 340-360 are not necessarily a good fit to use with VRF. So HRI, with help from the industry, developed a rating standard specifically for VRF equipment called HRI 1230. This standard defines the methods that all manufacturers must use when testing their equipment, under what conditions to operate that equipment when testing its performance, and what performance data must be published. With the rating standard in place, minimum efficiency thresholds were agreed upon and added to ASHRAE Standard 90.1. So HRI 1230 defines the common testing method and rating conditions for all VRF manufacturers, and ASHRAE 90.1 defines the required minimum efficiency thresholds for when these products are tested in accordance with HRI 1230. These minimum equipment efficiencies are part of the mandatory requirements in Standard 90.1, with tables for various families of equipment. As I mentioned, the tables for VRF equipment are relatively new, having just been introduced in the 2010 edition. For this type of equipment, the table includes both cooling and heating efficiencies, at full load and at part load. And as the standard clarifies, the selected equipment must meet all of these requirements. Here's an excerpt from the minimum equipment efficiency table in the 2010 version. These are the cooling efficiencies, listing both a full load EER and a part load IEER. you can see that the efficiency requirements are slightly less stringent for a heat recovery unit than for a straight heat pump. Now, these efficiencies did not change in the 2013 version of the standard. However, I should point out that there were errors in the published version of 90.1 2013, but ASHRAE published an errata sheet to fix those. The data shown on our slide is correct. And here's another excerpt from the table showing heating efficiencies. You can see that they are listed at two different operating conditions. Now, in the standard, the table also includes efficiency requirements for cooling-only units, water-cooled units, and equipment that uses either groundwater or a ground heat exchanger. Now, since we get questions on this often, let me pause a moment to explain some terms. SEER is a ratio of a season's worth of cooling produced divided by the same season's worth of energy used. It's sort of a blended efficiency number that attempts to encompass both full load and part load operation. EER is the ratio of cooling output at HRI standard rating conditions divided by the power consumed at those same conditions. It provides a full load efficiency metric. And IEER is a time-weighted efficiency calculation of 4 load conditions: 100, 75, 50, and 25%. It's an attempt to provide a single number part load efficiency metric. On the heating side, HSPF is basically the heating equivalent of SEER and is an attempt to encompass both full load and part load heating operation. COP is the ratio of heating output at HRI rating conditions divided by the power consumed. A unique term for VRF systems is SCHE, which is the simultaneous cooling and heating efficiency. It's included in the HRI rating standard 1230, but it's not included in 90.1. SCHE depicts the efficiency of a heat recovery unit when operating at a condition where the zone cooling loads and heating loads are very closely balanced. Now, in real buildings, this condition is probably rare, since commercial buildings tend to be cooling dominant. So the usefulness of SCHE is really to compare VRF products to each other to see how efficiently they actually do simultaneous heating and cooling. Now, there's a few things to think about when looking at standard ratings, regardless of the type of equipment. The primary value of a rating standard is to allow you to compare equipment within the same product family, regardless of manufacturer. For example, one VRF product to another, or one packaged rooftop unit to another. But they are not valid for comparing equipment from different families. For example, comparing the efficiency of a VRF product to a water source heat pump. Each product family has a different test standard, sometimes differing in their assumptions for operating conditions. In addition, they only cover that product, so the rating likely does not incorporate all energy users in the overall system. The 90.1 User's Manual includes some good discussion on this, some of which I've included as an extra slide in your handouts. Now, rating standards are also useful for setting code-mandated minimum efficiency thresholds for that given family of equipment, as we've seen in Standard 90.1. But they are not always a useful depiction of how that equipment will actually operate in your building. Just because they're called standard rating conditions does not mean that the equipment will actually operate at those conditions in a specific application. For example, the cooling rating conditions for VRF equipment assume air enters the indoor coil at 80 degrees dry bulb and 67 degrees wet bulb. If unconditioned outdoor air is delivered to the inlet of each indoor unit, where it is then mixed with recirculated air from the zone, then your system might operate at this condition. However, if the outdoor air is first conditioned by a dedicated outdoor air unit, the entering air conditions will be quite different. Comparing products from different families or estimating the performance in an actual building really requires a whole building energy simulation like TRACE. So let's move on to another part of 90.1 that we get questions on, and that's the fan power limitation. Standard 90.1 prescribes a limit on fan power based either on the nameplate horsepower or system brake horsepower, as shown in this table. However, it's important to note that the requirements of this section only take effect when the fan system exceeds 5 horsepower. In this case, each indoor VRF terminal is considered a separate fan system. And since it's unlikely that a single indoor unit will have a motor larger than 5 horsepower, this fan power limitation rarely applies to a VRF system. However, it is a bit more complicated since you need to consider all the fans in a system. For example, the fan power used by the dedicated outdoor air unit must be allocated to the individual VRF terminals on a CFM weighted basis. There's an example in the 90.1 user's manual that explains this. Even so, it would still be unusual to exceed the 5 horsepower threshold. The next requirement we'll discuss is for economizers. The standard 90.1 requirement for an economizer depends on system size and climate zone. In the 2010 version, either an air or water economizer is required on each system 4.5 tons or larger, in every climate except Zone 1. But just like in the case of the fan power limitation, each indoor VRF terminal is considered a fan cooling unit. So if an indoor VRF unit is smaller than 4.5 tons, which is typically the case, an economizer is not required. In your handouts, I've included an excerpt from an example in the 90.1 user's manual that explains this. So what if an indoor VRF unit is larger than 4.5 tons? An airside economizer is pretty hard to install in a VRF system because the outdoor air duct would need to be sized to deliver 100% of the design supply airflow. Usually the dedicated outdoor air system is sized to deliver only the minimum ventilation required. And a waterside economizer is typically not an option, but there are other exceptions in the standard. For instance, exception I exempts you from having to provide an economizer if the cooling efficiency of the VRF equipment is sufficiently higher than the minimum required by the standard. How much more efficient the equipment must be depends on the climate zone, as depicted by this table from the standard. For climates with more potential hours for economizing, the cooling equipment has to be even more efficient to justify being exempt from providing an economizer. For example, in climate zone 5A, which includes the northern halves of Illinois, Indiana, and Ohio, the IEER of the VRF system would need to be 49% higher than the minimum required IEER in order for the economizer to be eliminated. Today, most VRF manufacturers offer products that can meet these elevated IEER thresholds. So even if an indoor VRF unit exceeds 4.5 tons, you can still be exempt from the economizer requirement by installing higher efficiency equipment. The last 90.1 topic is exhaust air energy recovery. Similar to economizing, the standard 90.1 requirement for energy recovery depends on the system size and climate zone, but also on the percentage of outdoor air. The most common interpretation of this table is that if a 100% outdoor air system is installed, the furthest right column applies. In this case, if the project is in a humid climate, designated as A, or one of the coldest climates, 7 or 8, then the dedicated outdoor air system must have exhaust air energy recovery. In the drier or marine climates, the system will require energy recovery once it reaches the airflow threshold listed in this table. In the 2013 version, this table changed, but the thresholds for 100% outdoor air are the same except for in the most mild dry climates.
So to summarize what I heard, 90.1 includes minimum efficiencies for VRF equipment, but it's unlikely that the indoor unit fan will exceed the 5 horsepower threshold, so the fan power limitation likely does not apply. For the same reason, economizers are probably not required due to the small size of the VRF terminals. but exhaust air energy recovery is probably going to be required in the dedicated outdoor air unit.
That's right. And remember, while rating standards are useful for setting minimum efficiency thresholds, they are not useful for comparing equipment from different families. Comparing different system types really requires a whole building energy simulation like Trace. Let's move on to the issue of ventilation. While not as frequent as the first two standards, we also get some questions about applying VRF with respect to standard 62.1, the ventilation standard. Like 90.1, there's a long list of requirements in standard 62.1, so I'm just going to discuss a few of the common questions we get related to VRF. I'll start with the distribution of the outdoor air to individual zones. Then I'll wrap up with demand control ventilation. Standard 62.1 defines how much outdoor air is required in each zone. The challenge for the design engineer is how to distribute that amount of outdoor air to the individual zones. This slide shows three common ways in which outdoor air is delivered in a VRF system. The left-hand zone shows outdoor air delivered to the ceiling plenum near the intake of a concealed indoor VRF terminal. The outdoor air mixes with the recirculated air in the plenum before being drawn into the terminal. The center zone shows the outdoor air ducted directly to the indoor terminal. This diagram shows a cassette-style unit, which often includes a knockout for connecting the outdoor air duct to it. But this approach could also be used with a concealed unit if the outdoor air duct connecting to the mixing box or a short section of ductwork mounted to the inlet. Finally, the right-hand zone shows the outdoor air delivered directly to the zone. In this case, a high-wall VRF terminal is mounted in the space, but this configuration could be used with any style of indoor unit. Let's take a moment to discuss the advantages and challenges of each approach. Probably the main advantage of delivering outdoor air to the plenum is that it avoids some of the cost and space needed to install the additional ductwork or diffusers that would be required if the outdoor air were ducted directly to each zone or unit. However, it's difficult to ensure that the required amount of outdoor air reaches each zone since it's not ducted directly. In addition, since the fan inside the VRF terminal is used to deliver outdoor air to the zone, that fan must operate whenever the dedicated outdoor air system is operating. Finally, if the outdoor air will be delivered to an open ceiling plenum, the dehumidified outdoor air typically cannot be delivered at a cold temperature. In most cases, it may need to be reheated above the expected dew point inside the building to avoid condensation on surfaces within that plenum. Standard 62.1 contains some words of caution about this configuration and emphasizes that if this approach is used, the engineer needs to ensure that each space receives its required minimum ventilation airflow. And the 62.1 User's Manual gives some specific guidance on how to and how not to design this type of system. The diagram on the left clarifies that the outdoor air duct needs to deliver the air near the intake of each indoor unit, not just into some far corner of the ceiling plenum. And it must include some means of balancing to make sure the right amount of air gets to each unit. Let's move on to the second configuration, where the outdoor air is ducted directly to each indoor unit rather than to an open plenum. The main advantage of this configuration is that it helps ensure that the required outdoor airflow reaches each zone, since it's ducted directly to each unit. And this approach helps ensure the outdoor air is adequately dispersed throughout the zone because it's distributed by the local fan through a common set of diffusers. However, for some types of indoor VRF terminals, this approach may require a field fabricated mixing box or a short section of duct where the outdoor air duct can connect and mix with recirculated air. In addition, since the local fan is used to deliver outdoor air to the zone, it must operate continuously whenever ventilation is needed during occupancy. If you cycle the indoor fan on and off, or if you vary its speed, less outdoor air will be delivered to the zone. So to ensure that you get the required outdoor airflow, you either need to run the indoor unit fan at a constant speed, or you could add a pressure-independent damper like a VAV box to the outdoor air duct. Then as the indoor fan speed changes, this damper opens or closes to maintain the same outdoor airflow regardless of fan speed. Now, Standard 62.1 speaks to this concern by emphasizing that the ventilation air distribution system needs to provide each space with its minimum ventilation airflow under any load condition. The final configuration is to duct the outdoor air directly to each zone. One advantage of this approach is that it's easy to ensure that the required outdoor airflow reaches each zone, since it can be measured through the dedicated diffusers during the balancing process. And this approach affords the opportunity to cycle the indoor fan on and off, or vary its speed at part load. This is possible because the outdoor air is not distributed to the zone through that indoor fan. Finally, this configuration offers the opportunity to deliver the outdoor air at a cold temperature, rather than reheated to neutral, which would allow for downsizing of the VRF units. Of course, there are also drawbacks to this configuration. It typically requires the installation of additional ductwork and separate diffusers. And multiple diffusers may be needed to ensure that outdoor air is adequately dispersed through a larger zone. So I talked about how the outdoor air gets to the zones, but what about where it comes from? I suppose in some cases the outdoor air might be unconditioned and ducted directly to the indoor units. It's simple, but this practice should probably be limited to just the dry, mild climates. In other applications, an energy recovery ventilator might be used. This reduces the ventilation load, but requires an exhaust air path and extra fan. And it does not dehumidify the outdoor air to a dew point that's drier than the space. In most applications, the use of a dedicated outdoor air unit is preferred, since it can adequately dehumidify the outdoor air and not rely on the VRF terminals to have to do so. Often these are standalone air-cooled DX units like the example shown here. These are simple to design in that they do not affect the sizing of the VRF system. And they can be operated for after-hours humidity control without the need to operate the VRF. But other systems use an air handler where the DX coil is connected to a VRF system. This can allow for simultaneous cooling and heat recovery during colder months, if the system also serves interior zones that still require cooling, while the outdoor air must be heated. However, remember that in the summer, both the outdoor air unit and indoor units will be in cooling, so you're limited on the circuit size. And at least today, there's often a low limit on how cold of air can be heated, possibly requiring the addition of preheat. Now, the last topic I'll discuss related to Standard 62.1 is demand-controlled ventilation. The standard allows zone outdoor airflow to be dynamically reset based on changing zone population. And it provides some details on implementation. First, the controls can't reduce zone outdoor airflow any lower than the area outdoor air rate, R sub A. Second, when the system is dehumidifying, the intake airflow cannot be reduced to a level that's lower than the coincident exhaust airflow from the system. This requirement indirectly addresses building pressurization. And finally, all assumptions must be documented. This includes control sequences, min and max airflows, and set points. Now, for a VRF system, DCV is most likely implemented by adding dampers to the outdoor air ductwork and sensors to those zones where demand control ventilation will be used. In this example, pressure-independent VAV terminals are added to the outdoor air duct. This allows outdoor airflow to be measured and varied based on a CO2 sensor, a time-of-day schedule in the automation system, or even a simple occupancy sensor. Of course, this also requires that the dedicated outdoor air unit be able to handle variable airflow.
So let me summarize what I heard. I learned that there are several ways to distribute outdoor air to the individual spaces, but it sounds like you probably prefer ducting it directly to each space, right?
Yeah, whenever possible. That way you know the outdoor air is getting where it's supposed to be. And you can save energy by cycling or varying the speed on the indoor unit fan. It also lends itself well to adding VAV boxes for demand control ventilation and further energy savings.
And you would deliver the dehumidified outdoor air cold rather than reheated?
In most cases, yes. That allows you to downsize the VRF units and save energy by taking advantage of the sensible cooling you already paid for in the process of dehumidifying the outdoor air.
Okay, let's move on to VRF zoning. Zoning involves selecting an indoor unit to offset the heating and cooling load for a given zone or space. For a VRF system, it is the process of assigning multiple indoor units to an outdoor unit with the goal of minimizing first cost and energy cost while maintaining indoor comfort. This is a complicated task, to say the least. Without proper zoning, performance and cost will both be sacrificed. Each VRF manufacturer has software that allows the user to enter zone loads, choose indoor products, and assign indoor products to select outdoor products. Once complete, the software will output a bill of materials and piping layout. In order to optimally zone a VRF system, it's necessary to know the design, heating, and cooling load in each zone. Designers can still zone a system without the loads, but the performance will not be optimized and comfort could be sacrificed. Good zoning allows the choice of a heat pump or heat recovery system. As was explained earlier, the VRF heat recovery unit can provide heat to some zones while providing cooling to others. But the VRF heat pump will only heat or cool its zones and stay in either heating or cooling until all zones are satisfied. Only then the heat pump will be allowed to switch mode and attempt to satisfy the other zones. So, zones of a heat pump system must be similar in load characteristics in order to maintain comfort. Let's look at an example office building that will use a VRF system. This building is too large for a single VRF system to handle it, so we'll need to divide the building into zones that match outdoor unit capacity. If we zone this building to use heat pump VRF systems, the zones connected to the outdoor unit must have common heating and cooling needs. If not, the zones that require cooling will be uncomfortable during the time the outdoor unit is attempting to satisfy the zones that require heating and vice versa. So it's necessary to break up the building into zones of similar daily and annual load profiles. Offices 110 through 113 on the north wall of the building are likely the same load throughout the day and year, so they would be potential candidates for a single heat pump system. Coupling offices 106, 107, and 108 on the east side with offices 115, 116, and 117 on the west side would probably make a poor choice due to the daily changes in load as the sun rises and sets and the inability of the heat pump VRF unit to simultaneously heat and cool. However, a heat recovery VRF system can heat and cool zones simultaneously, and they can use the recovered heat from one zone in cooling to heat another zone. The ultimate goal of zoning a heat recovery system would be to equalize the cooling and heating loads on the same heat recovery system. Coupling the east and west offices from the previous example on one heat recovery system will likely result in some savings in simultaneous heating and cooling. However, this requires longer and more extensive refrigerant piping, and as Dave mentioned, can be challenging in terms of compliance with ASHRAE Standard 15. Another possibility is to couple the interior zones and the dedicated outdoor air unit on a single VRF heat recovery system. In the summer, they will all require cooling, so the sizing will be dictated by the sum of all the loads. In the winter, the indoor cooling load and the fresh air heating load can be used to offset each other, and energy savings can be realized. Zoning is difficult, but modeling tools might make it easier. They can certainly help with determining annual design cooling and heating loads. So let's talk about building simulations and VRF for a bit. Today, building simulation is used to show compliance with industry building standards and codes, make system comparisons, and use for green ratings. While variable refrigerant flow systems have existed since the 1980s, VRF energy simulation has continued to evolve. Prior to the introduction of the standardized performance rating method in HRI 1230, design and rating conditions for VRF equipment varied. This could pose a problem for simulation programs if extrapolation was needed to operate equipment beyond the provided rating conditions. So here's our building again. The building is located in Philadelphia, Pennsylvania, and has a design cooling load of about 70 tons and a design heating load of about 350 MBH. The building has been designed to comply with ASHRAE Standard 90.1/2007. Of course, a portion of the load is from ventilation, and with VRF systems, a separate outdoor air system is often used for this ventilation load. In our simulation, we'll use a separate DX dedicated outdoor air system, which is fairly common. In the simulation, the outdoor air is being delivered directly to the spaces at or near room neutral conditions. It is being dehumidified to a dew point of 55 degrees and reheated to 71 degrees Fahrenheit. With this system in place, the cooling load that must be handled by the VRF system is reduced to 51 tons and the heating load is reduced to 138 MBH. It's interesting to note that for this building, roughly a third of the design cooling load and nearly 2/3 of the design heating load are from ventilation. Let's look at some zoning alternatives. Earlier, I zoned the model by inspection, but with load design software, I can determine the design cooling and heating load for each zone, then pair it with the other zones and an outdoor unit. If the software you're using is also able to provide building and system load profiles, it makes heat pump and heat recovery equipment selection easier. Using these load profiles and the software, I can mix and match zones together to take better advantage of heat recovery. And here's a thought. For heat pump systems, consider using temperature profile reports and unmet load hours as an indication to determine if a specific zone has been properly grouped with others. A high number of unmet hours for a specific space might show that it has been grouped with other spaces that have a dissimilar load profile. Likewise, an erratic temperature profile from the simulation might hint at improper zoning. This example report shows an office on the 3rd floor, Office 117. The office seems to be experiencing a high number of unmet load hours for cooling, which suggests that it might have been improperly zoned. It also looks like there are a high number of hours in the 80 to 85 degree range. This specific zone might not be a good candidate for the VRF Heat Pump West system. Let's get back to our example building. We can use simulation software like the Tray 700 program to size indoor units and identify which zones to group together on the same system. In this case, we could group all of the zones together on a single VRF system. This is actually one of the more common mistakes we see. Remember that the total load, excluding ventilation, is 51 tons and greater than a single VRF outdoor unit can provide. We'll need at least 2 systems. So we can split the building into a couple of systems like I showed earlier. Based upon the building's location and loads, the building will probably require 3 or 4 systems. I might group the corners together to take advantage of heat recovery opportunities. I could put the zones on the northwest and southeast together and the northeast and southwest together. The remaining interior zones might be best served by a heat pump system since they will likely need cooling year-round with only morning warm-up. Like the example from a few minutes ago, you might run into trouble with respect to ASHRAE Standard 15 requirements if refrigerant piping crisscrosses the building. If the zoning makes sense, we can now use the software's output reports to select equipment using the VRF manufacturer's selection software. We could also continue with an energy analysis. So after simulating the building with several zoning configurations, heat pump VRF and heat recovery VRF, we reviewed the output. As I mentioned earlier, much of the design heating load for this building is from the outdoor air for ventilation and is not handled by the VRF system. Remember that in this instance, a separate dedicated outdoor air unit handles the ventilation load. The remaining building heating load is largely from morning warm-up. This limits the benefit of heat recovery VRF. If the VRF system and the outdoor air system were coupled, that is, if the outdoor air system contained a refrigerant coil attached to the VRF system, heat recovery might show more of a benefit during cold weather. This would allow heat to be transferred from the interior spaces that need cooling to the refrigerant coil in the dedicated outdoor air unit, which is heating the outdoor air. Of course, coupling the outdoor air unit to the VRF system will affect VRF outdoor unit selection and sizing. Because this wasn't the case for the specified building, there were a limited number of hours where simultaneous heating and cooling could occur. With respect to VRF, there are 2 paths you can go by. but in the long run, carefully evaluate the loads and needs of the building to determine whether the heat pump or heat recovery variant works best for your given project. You can use simulation software to help answer these questions. So we've seen that VRF systems are complex with a lot of variables. They can have one or more outdoor units, multiple indoor units, and sophisticated refrigerant routing systems. There are some aspects of these systems that are not currently modeled or have limitations. Each simulation program has its own unique limitations. Let's look at some challenges and considerations when modeling VRF systems. Generally speaking, not all simulation programs are capable of modeling VRF or various forms of it. In fact, there are some simulation programs that are not able to model VRF at all, and users may seek workarounds based upon another system that is available in the simulation program. Caution should always be exercised when using workarounds, even if they're prescribed, because unique aspects of system operation may not be captured. Here's a list of potential challenges when modeling VRF systems that we'll explore. And don't forget the issue raised earlier where a single VRF system is modeled that serves the entire building load, even if the building load is larger than a single VRF system. The system can be air-cooled, water-cooled, ground-coupled, and multiple units can be piped or ganged together. Many simulation programs can model air-cooled VRF systems, but water-cooled modeling is less common. With ground-coupled units, the program will need to model both the water-cooled aspect and be capable of accounting for the source of the groundwater, whether it's through an aquifer or well field. In either case, don't forget to account for any heat transfer losses due to the addition of glycol and a refrigerant to water heat exchanger in the loop. Defrost operation allows the outdoor unit to remove any frost and ice buildup on the outdoor coil when operating in the heating mode. Remember that the heat exchanger in the outdoor unit serves as an evaporator when the system is predominantly heating, and this usually occurs when it's cold outside. If a single outdoor unit is used, the system will operate in cooling mode for several minutes, so hot refrigerant is routed to the outdoor unit to melt any built-up ice or frost. Of course, when this occurs, the indoor unit discharges cool air into the space regardless of demand. If multiple outdoor units are used, they may be piped together, and the defrost operation may be different with the additional outdoor unit. Even if the program does model the energy impact of defrost, the change in indoor temperature from defrost operation may not be included in the simulation. The occurrence of the defrost operation may be infrequent, which would limit the impact on the results. Earlier I mentioned that VRF system piping can be quite long. As with other fluids, losses are incurred throughout the piping system. Some simulation programs include losses from the piping, while others do not. With large piping lengths, the total system capacity can be reduced, and this may not be included in the simulation program. Each manufacturer has their own degradation information, so the modeler may need to manually account for this. You can see an example of the capacity correction coefficients for the heating mode from one manufacturer in the table. Remember the oil recovery or flush cycle that Paul talked about earlier? Any oil that has made it past the oil separator must be periodically recovered. During the oil recovery operation, the system's ability to provide conditioned air is limited, which will affect the space, temperature, and load. This is something that is difficult for simulation programs to estimate because the operations are unique to system manufacturers and oil recovery cycle durations vary. Like any other equipment simulation, it's critical to enter correct energy rates for VRF equipment. With VRF equipment, the rates provided may be combined. This means that the compressor, condenser fans, and indoor fan powers may be summed and reported as a single energy rate. If the simulation program models the compressor, indoor fan, and outdoor fans independently, you may need to break the components out from a packaged rate and enter them separately. Oftentimes, we'll see users model a packaged energy rate which contains heat rejection fan power and then model a separate heat rejection component. In essence, the condenser fan power is being accounted for twice. Some simulation programs have the ability to automatically break the energy rates out based upon user-specified indoor and outdoor fan power. Check with your software vendor to see which components are simulated and how. From there, you should be able to determine which component energies should be entered into the simulation. Finally, each VRF manufacturer creates their own proprietary system control algorithms. VRF systems may operate differently from one manufacturer to another. This means that simulation programs are not able to exactly replicate how the entire system is controlled. The individual zone control may be difficult to mimic in the simulation since it's hard to predict what each occupant is going to do with their own remote control. So in summary, modeling VRF systems is possible as long as you understand the simulation program's capabilities. Some energy simulation programs are not able to model all variations of VRF, including water-cooled, ground-coupled, or multiple outdoor units ganged together. If the programs can model VRF systems, they may not fully model defrost operation, account for long piping lengths and associated system capacity degradation, or oil recovery operation. VRF system control will be difficult to model because it's proprietary. Finally, be careful when using VRF system workarounds. There is ongoing research to improve VRF models in many simulation programs, which should yield an even more accurate model in the future. Jeannie, can you bring us on home?
We packed a full program and hopefully gave you a better understanding of applying VRF systems. Every system has its benefits, and everyone has its unique set of challenges to apply properly. Some projects might be a good fit for using VRF, while others it might not be the best fit. In many locales, ASHRAE standards 15, 90.1, and 62.1 are commonly used. Hopefully our discussion today helped you learn more about how to comply with these standards when using a VRF system through careful system design and equipment selection. And we discussed how zoning impacts the performance of both heat pump and heat recovery VRF systems. And finally, energy simulation tools are available, but may have some shortcomings when it comes to modeling certain aspects of VRF system operation. There are a number of publications available that provide more information on the material covered today, including an engineer's newsletter article on VRF. A bibliography detailing these resources is included in your handout. Additionally, all past broadcasts are available on DVD at trane.com/ENL. All are accredited for continuing education, and many are available on demand free of charge. Visit trane.com/continuing education for a complete list to satisfy credentialing requirements. Many are lead specific. Remember to fill out a survey and let us know how we're doing. AIA members, please remember to turn in your member information to your local site coordinator. And finally, please ask your local host about details when we return in fall to discuss chilled water terminal systems. We hope you'll join us again, and thanks for your time today.